The Orion constellation has been a celestial landmark for thousands of years, guiding ancient civilizations and modern astronomers alike. But what if I told you it hides secrets far stranger than we ever imagined? From unexplained energy signals to potential alien megastructures, Orion's mysteries defy our understanding of space. Could this familiar pattern of stars hold clues to cosmic phenomena we've yet to discover? Join us as we unravel the enigmas lurking in one of the night sky's most iconic formations. Before we begin, comment with what constellation interests you the most. Like the video and subscribe if you want more videos like this one. Let's begin. Picture yourself beneath a Babylonian night sky 4 millennia ago, tracing the same three-star belt we recognize today. Orion's distinct hourglass shape made it one of the most universally identified constellations across ancient cultures, despite their geographical isolation. The Egyptians saw Osiris, their god of resurrection, in those stars. Half a world away, Greek storytellers envisioned a mighty hunter pursuing the Pleiades through the heavens. What's striking isn't just that civilizations independently recognized Orion's pattern, but how they connected these stars to stories of deities and cosmic cycles. The Maya aligned their temples with Orion's rising, using it to track agricultural seasons. Halfway across the globe, builders positioned the Great Pyramid's air shafts to frame Orion's belt around 2500 BCE. This wasn't mere coincidence. The constellation served as a synchronizing marker for events ranging from Nile floods to Mesoamerican planting cycles. The parallels become more intriguing when we examine mythologies. Multiple cultures associated Orion with death and rebirth themes. Egyptian texts describe Osiris traveling through the Duat, their celestial afterlife realm corresponding to Orion's position. Siberian shamans considered Orion the world tree, connecting earthly and spiritual realms. These shared motifs raise questions about whether early astronomers preserved fragments of lost astronomical knowledge through oral traditions. One practical explanation stands out. Orion dominates the winter sky across both hemispheres, its bright stars visible even in light-polluted ancient cities. Betelgeuse and Rigel formed clear reference points for navigation long before compasses existed. The constellation's position directly opposed the sun during summer months, making it a reliable seasonal marker for early agricultural societies. This functional utility likely contributed to its cross-cultural significance. The Nebra sky disk, dating to 1600 BCE, shows one of the earliest known European depictions of celestial patterns, matching Orion's configuration. Meanwhile, in the American Southwest, ancestral Puebloans painted star clusters resembling Orion on canyon walls. These independent recognitions suggest something fundamental about how human brains process stellar patterns. We're wired to connect dots into meaningful shapes. Modern analysis reveals subtle differences in how cultures interpreted Orion's stars. Some African traditions saw the belt as 3 zebras, while Aboriginal Australians envisioned a canoe filled with fishermen. The shared foundation remains striking. Humans consistently selected the same bright stars from thousands of dimmer ones, projecting their worldview onto this cosmic canvas. Archaeoastronomers have identified at least 37 major ancient sites with Orion alignments, from Stonehenge to Chichen Itza. The Hopewell culture in North America built earthworks mirroring Orion's proportions around 200 CE. These widespread architectural references imply the constellation served as more than just a pretty pattern. It functioned as a celestial clock and spiritual compass. Today's astronomers uncover new layers to Orion's significance through infrared telescopes and spectral analysis. But the ancient observers knew something we often forget. Constellations aren't just scientific subjects, but cultural artifacts, connecting us to generations of stargazers. Their myths encoded practical knowledge about timekeeping, navigation, and humanity's place in the cosmos. When we look at Orion tonight, we're seeing more than a chance arrangement of luminous objects. We're witnessing one of humanity's oldest continuous traditions, a celestial heirloom passed down through hundreds of generations. The same stars that guided Bronze Age navigators still shine above us, unchanged in their configuration, but constantly revealing new secrets to those who study them, with both telescopes and an appreciation for ancient sky wisdom. Orion's familiar shape appears simple from Earth, just bright dots forming a hunter's outline. But this celestial connect the dots image disguises a complex reality. Each star in Orion exists at vastly different distances from us, unrelated except by our line of sight. The constellation we perceive is essentially a trick of perspective. Betelgeuse, the red supergiant marking Orion's shoulder, sits about 550 light-years away. Meanwhile, Rigel, the blue-white star at his foot, lies nearly twice as distant, at 860 light-years. This means, if we could view Orion from another angle in space, its iconic shape would completely dissolve. The stars have no physical connection. They simply align from our vantage point. The color difference between Betelgeuse and Rigel reveals their contrasting life stages. Betelgeuse glows orange-red because it's old and bloated, having expanded to about 700 times our Sun's diameter. In astronomical terms, it's nearing the end of its life and could explode as a supernova within the next 100,000 years. Rigel represents the opposite extreme, a young, massive blue supergiant, burning hot and bright. Their contrast demonstrates how constellations mix stellar generations. Orion stars also vary dramatically in size and power. Bellatrix, the shoulder star, shines with 4,000 times the Sun's luminosity. The belt stars, Alnitak, Alnilam, and Mintaka, are all multiple star systems, with companions too close to distinguish with the naked eye. Alnilam, the middle belt star, puts out 375,000 times more energy than our Sun, despite being only 16 to 20 times more massive. These stars aren't just scattered randomly through space. They trace part of the Orion Arm, our local spiral arm in the Milky Way. Measurements show many share similar motion vectors, suggesting a common origin in the same interstellar cloud. Their arrangement gives astronomers a cross-section view of stellar evolution, from newborn stars still embedded in nebulas to aging giants nearing explosive deaths. The distances between Orion stars make clear why constellations are human inventions rather than natural groupings. Light travels from Mintaka to Earth in about 1,200 years, but needs 1,800 years to reach us from Saiph, another corner star. This means when we look at Orion, some stars' light left when Rome ruled Europe, while other light departed during the Viking Age. The constellation spans centuries of cosmic history in a single view. Modern astronomy reveals more about these individual stars than ancient observers could imagine. We now know Betelgeuse has surface convection cells larger than our solar system, with temperatures varying by thousands of degrees across its uneven surface. Rigel's stellar wind blows at nearly 2,000 kilometers per second, shaping surrounding nebulas with its intense radiation. These details highlight how even familiar stars hold surprises when examined closely. The variety within Orion makes it ideal for studying stellar life cycles. Its bright stars represent different mass categories that experience distinct fates, becoming supernovas, neutron stars, or black holes. Fainter stars in the pattern include main sequence suns like our own, and failed stars called brown dwarfs. This cosmic laboratory lets astronomers compare how stars of various sizes evolve over time. Looking deeper, we find Orion contains objects invisible to ancient skywatchers. Infrared observations reveal thousands of cooler stars hidden between the bright ones. Many are young stellar objects still gathering material from surrounding disks. Some show evidence of forming planetary systems. The constellation includes protostars, stellar nurseries, and remnants of dead stars, entire generations of cosmic life cycles compressed into our two-dimensional view. This stellar menagerie demonstrates how constellations mix objects that have nothing physically in common. Orion's stars differ in age, distance, and composition. They simply happen to lie along the same sightline from Earth. This reality check doesn't diminish the constellation's beauty, but adds depth to our understanding. When we look at Orion, we're actually peering through layers of cosmic time and space. Behind Orion's visible stars lies an invisible structure astronomers call the Orion Molecular Cloud Complex. Viewed through infrared telescopes, this vast region reveals itself as a tapestry of glowing gas and dust stretching across hundreds of light years. These cold, dark clouds appear empty to our eyes, but they contain enough material to form thousands of new stars. The cloud complex contains several distinct regions, each with unique properties. The Orion A and B molecular clouds serve as the primary stellar nurseries, while the Lambda Orionis ring forms a protective shell around them. Temperatures within these clouds hover just 10 to 20 degrees above absolute zero, allowing hydrogen molecules to clump together under gravity's pull. This slow accumulation marks the first step in star formation. Hubble's observations show dozens of protostars embedded within the cloud's dense cores. These infant stars appear as bright knots surrounded by swirling disks of gas, future planetary systems in their earliest stages. Some disks show gaps where fledgling planets have begun clearing their orbits. The images prove star formation remains an active process in Orion, not just a relic of the distant past. What makes Orion's clouds unusually productive compared to other molecular clouds? Measurements indicate a higher concentration of dense gas clumps here than average. The cloud contains about 100,000 solar masses of material, with some regions packing 1 million molecules per cubic centimeter. Nearby, young stars also contribute by bombarding the cloud with radiation that compresses gas into tighter knots, triggering new rounds of starbirth. The trapezium cluster's massive stars play a key role in shaping their birthplace. These brilliant youngsters blast the surrounding cloud with stellar winds reaching 2,000 kilometers per second. The resulting pressure carves out cavities, while simultaneously squeezing adjacent gas to critical densities. This feedback process explains why Orion produces stars at nearly 10 times the rate of typical galactic clouds. Radio telescopes detect complex organic molecules floating within these interstellar clouds. Compounds like methyl cyanide and vinyl alcohol shouldn't survive harsh space conditions, yet they're abundant here. These molecules form on dust grains that serve as microscopic chemistry labs. Some researchers speculate similar clouds could have seeded early Earth with prebiotic ingredients. The nebula's dynamic environment creates stars with a wide mass range. While most form as modest red dwarfs, Orion regularly produces massive blue stars that influence their surroundings. This balance makes it an ideal analog for studying how star-forming regions shaped our own solar system's development. The cloud's conditions likely resembled those where our Sun was born 4.6 billion years ago. ALMA telescope observations reveal intricate structures within protoplanetary disks. Some show spiral arms similar to tiny galaxies, while others exhibit concentric rings where planets may be assembling. These details help astronomers connect the dots between collapsing gas clouds and mature planetary systems. Orion's youth means we're seeing processes that occurred in our solar neighborhood before Earth formed. Surprisingly, the cloud complex extends far beyond the visible nebula. Radio maps show filamentary structures reaching into neighboring constellations. These faint tendrils contain enough cold hydrogen to form additional stars for millions of years. Some filaments stretch over 150 light years, tracing the magnetic field lines that guide material flows throughout the region. Star formation here follows a rhythm astronomers are just beginning to understand. Rather than occurring steadily, it seems to happen in bursts, triggered by external shocks. Collisions between different cloud components or shockwaves from nearby supernovae can initiate rapid collapses. This episodic behavior suggests stellar birth isn't as continuous as once thought. The Orion clouds offer more than just star formation insights. They serve as a natural laboratory for studying physics under extreme conditions. Turbulent gas motions within them approach supersonic speeds, while magnetic field strengths reach milligauss levels. These parameters can only be approximated in terrestrial labs, making the cloud an invaluable cosmic testbed. Certain emissions from the cloud continue to puzzle researchers. Some sub-millimeter wavelength signals don't match known molecular transitions. Others appear too energetic for the region's measured temperature. These anomalies hint at undiscovered chemical processes, or possibly new physics operating within dense interstellar environments. On March 12, 2007, radio telescopes detected something extraordinary from Orion's direction. A pulse of energy, lasting just 5 milliseconds, packed more power than the Sun radiates in 300,000 years. This event, catalogued as FRB 070312, joined a growing class of phenomena called fast radio bursts. But its origin, within a familiar constellation, made this detection particularly intriguing. The signal's characteristics defied easy explanation. Its dispersion measure, how much interstellar material slowed different frequencies, suggested it traveled through considerable gas and dust before reaching Earth. Yet no known object in Orion matched both the energy output and rapid timescale. The pulse showed no repetition in follow-up observations, unlike some later discovered repeating FRBs. Astronomers proposed several natural explanations for the Orion burst. A magnetar, a highly magnetized neutron star, could produce such energetic pulses, during starquakes on its rigid crust. Alternatively, two compact objects like neutron stars merging would release tremendous energy in gravitational waves and electromagnetic radiation. Both scenarios fit parts of the observation, but left gaps in full explanation. Researchers also examined whether the burst might have originated beyond Orion, with the constellation merely lying along its path. The signal's dispersion suggested it came from cosmological distances, implying an energy release rivaling some supernovae. This raised questions about why we haven't detected more similar events, if they're so powerful. Follow-up studies using the Very Large Array and other facilities failed to locate any persistent radio source at the burst's coordinates. Nor did optical and X-ray telescopes find afterglows that often accompany catastrophic cosmic events. The lack of counterparts made pinning down the source increasingly difficult. Some characteristics made the Orion burst unusual, even among FRBs. Its frequency structure showed complex subpulses lasting just microseconds. This fine detail survives the long journey through interstellar and intergalactic medium, suggesting an extremely compact emission region. An object would need to be smaller than 300 kilometers to produce such rapid variations. Theories about possible artificial origins gained attention due to the signal's peculiarities. A 2017 study noted that the burst's frequency drift resembled what might occur with a directed energy transmitter. However, most astronomers consider natural explanations more plausible, given the energy scales involved. The transmitter hypothesis requires technology far beyond human capability. New analysis techniques have provided fresh insights. Polarization measurements revealed that the burst's waves were nearly 100% linearly polarized. This suggests the radiation passed through a strong magnetic field, supporting the magnetar hypothesis. Yet no known magnetar exists in that region of Orion at the required distance. The European VLBI network attempted to pinpoint the burst's location with milli-arc-second precision in 2021. Their results placed it near a faint dwarf galaxy, but the association remains uncertain. Without detecting repeated bursts from the same location, establishing a definite host proves challenging. What makes this event particularly puzzling is its occurrence in such a well-studied region. Orion has been scrutinized across the electromagnetic spectrum for decades. If a hitherto unknown phenomenon can hide here, it raises questions about what else we might be missing in familiar cosmic neighborhoods. Surveys estimate that similar bursts likely occur thousands of times per day across the entire sky. Most go undetected because telescopes must be pointing in the right direction at exactly the right moment. New instruments like CHIME and DSA 2000 aim to catch hundreds more FRBs, potentially solving their mystery. Astronomers tracking stars near Orion's belt have noticed peculiar movement patterns that suggest an invisible gravitational force at work. Several stars exhibit unexpected accelerations, their paths bending as if orbiting something massive we can't see. The most likely explanation points to an intermediate mass black hole, a cosmic phantom weighing hundreds to thousands of solar masses. This class of black hole has proven elusive, with few confirmed detections across the galaxy. The evidence comes from precise measurements of stellar velocities. Near the Orion Nebula, multiple stars show motions that can't be explained by the visible mass in the region. Their trajectories imply a dense, compact object roughly 200 times the Sun's mass influencing their paths. Such an object would fit the predicted mass range between stellar black holes and supermassive ones at galactic centers. Intermediate mass black holes represent a missing link in our understanding of black hole formation. Stellar mass black holes form from collapsing stars, while supermassive ones anchor galaxies. But how the latter grow so enormous remains unclear. Finding mid-sized black holes could reveal whether they grow through mergers or accretion over time. Orion might hold the key to solving this cosmic evolution puzzle. Current gravitational wave detectors like LIGO and Virgo could potentially identify such an object through its interactions. While no confirmed signals have been detected from this region yet, future upgrades to these instruments may reveal subtle space-time ripples caused by the black hole's activity. The lack of emissions makes detection challenging. Without infalling material creating X-rays, the object remains dark across the electromagnetic spectrum. The black hole's location presents another mystery. It appears offset from the main star-forming regions where massive stars collapse into black holes. This suggests it could be a primordial black hole formed in the early universe, or perhaps a wanderer ejected from another part of the galaxy. Either scenario would challenge current models of black hole formation and distribution. Some researchers propose the unseen mass might instead be a tight cluster of smaller objects, perhaps neutron stars or stellar black holes. However, recent high-resolution surveys haven't found the concentration of compact objects needed to explain the observed gravitational effects. The cluster scenario also struggles to account for the precise orbital patterns seen. The Orion Nebula's position adds intrigue to the search. As one of the closest massive star-forming regions, it gives astronomers their best chance to study such phenomena in detail. If a black hole exists here, its relative proximity would allow unprecedented study of how these objects interact with surrounding gas and stars. This potential black hole could explain several Orion anomalies. Its gravitational influence might have shaped the peculiar motions of runaway stars like AE Aurigae and Mu Columbi. It could also contribute to the high-energy particle emissions detected from the region that currently lack clear explanations. Radio astronomers have identified a few faint point sources in the suspect area that warrant further investigation. These could represent emissions from hot gas spiraling into the black hole at nearly undetectable rates. Future observations with more sensitive arrays may confirm or rule out this possibility. The search benefits from new astrometric data from spacecraft like Gaia, which provides unprecedentedly precise stellar position measurements. By tracking stars over years, researchers can detect subtle wobbles that betray an unseen companion's gravitational pull. These techniques have already proven successful in finding hidden black holes elsewhere in the galaxy. Some theorists have explored alternative explanations involving dark matter concentrations. While possible, these would require unconventional dark matter behavior not predicted by standard models. The black hole hypothesis remains the most parsimonious explanation given current evidence. The hunt continues, with multiple approaches. Spectroscopy can reveal telltale Doppler shifts in stars orbiting an invisible mass. Millimeter-wave telescopes search for the small but distinctive disturbances such an object would create in surrounding dust clouds. Each method provides a different line of evidence towards solving the mystery. If confirmed, this would be among the closest known intermediate mass black holes to Earth, offering unique opportunities for study. Its environment differs markedly from the galactic centers where most such objects are sought, potentially revealing new aspects of black hole physics. For now, the phantom mass remains just outside our observational grasp, a persistent anomaly in astronomy's best-studied constellation. Its discovery would rewrite our understanding of black hole populations while solving several Orion mysteries simultaneously. Until then, it exists as a gravitational whisper among familiar stars. Meanwhile, another Orion puzzle draws astronomers' attention: the erratic behavior of Alnitak, the easternmost belt star that refuses to follow expected stellar patterns. Alnitak, the easternmost star in Orion's belt, exhibits behavior that puzzles astronomers. This blue supergiant should pulse with predictable regularity, like similar stars. Yet its light variations follow no recognizable pattern. Instead of the smooth brightness changes characteristic of stellar pulsations, Alnitak's luminosity shifts abruptly, sometimes dimming by several percent over hours before snapping back to normal. These irregularities have persisted across decades of observation, resisting all conventional explanations. The star's spectrum adds to the mystery. Typical pulsating stars show consistent temperature fluctuations that correlate with their brightness changes. Alnitak's spectra reveal unexpected emission lines that come and go independently of its light curve. Some researchers have noted these anomalies resemble what might occur if something periodically passed between the star and Earth, but no orbiting companion large enough to cause such effects has been detected. Breakthrough Listen, the SETI initiative, included Alnitak in its 2017 survey of potential technosignatures. While the project found no definitive evidence of artificial signals, it did identify peculiar radio emissions that correlate loosely with the optical anomalies. The emissions show narrowband components that occasionally drift in frequency, a characteristic some interstellar communication schemes might employ. Most astronomers attribute this to natural plasma phenomena, but the coincidences remain intriguing. Pulsation models fail spectacularly when applied to Alnitak's behavior. Normally, massive stars like this exhibit radial pulsations driven by internal pressure changes, causing rhythmic expansions and contractions. Alnitak's variations look more like someone randomly adjusting a dimmer switch. The changes don't match known instability mechanisms for hot stars, nor do they align with binary star interactions. Even exotic explanations involving star spots or magnetic disturbances struggle to account for the full range of observations. Spectropolarimetry reveals another layer of strangeness. Alnitak's magnetic field appears more structured than typical for its stellar class, with localized knots of intense magnetism. These regions could potentially influence the star's outer layers in unusual ways, but current models can't explain how they'd produce the observed photometric behavior. Some theorists speculate we might be seeing the effects of a recently merged stellar companion, though supporting evidence remains scarce. Multi-wavelength observations complicate rather than clarify the picture. X-ray monitoring reveals occasional flares that shouldn't occur in stars of Alnitak's type. Simultaneous ultraviolet and optical measurements show inconsistent timing relationships between different wavebands. In most variable stars, these emissions rise and fall together, but Alnitak's appear partially decoupled, like different parts of the star operate on independent clocks. The star's rapid rotation offers one potential clue to its oddities. Spinning near its breakup velocity, Alnitak likely has an oblate shape, with significant equatorial bulging. This extreme rotation could distort normal pulsation modes or generate unusual surface dynamics. However, similar rapidly rotating stars don't exhibit comparable variability, suggesting rotation alone doesn't explain Alnitak's behavior. Radio interferometry has mapped Alnitak's immediate surroundings in detail. ruling out most environmental explanations. There's no evidence of obscuring dust clouds or nearby objects that might cause the observed flickering. The star's wind creates a typical bow shock as it plows through interstellar space, with no peculiar features that could account for the anomalies. Whatever causes Alnitak's strangeness appears intrinsic to the star itself. Photometric surveys dating back to the 1950s show the irregular variations have persisted for at least 70 years. There's no clear periodicity to the changes, though some statistical analyses suggest weekly repeating patterns every few months. If these represent genuine cycles rather than random fluctuations, they might hint at some undiscovered internal process within massive stars. Astroseismology, which studies stellar interiors through vibrational patterns, hits a wall with Alnitak. The usual techniques for deciphering a star's internal structure from its pulsations prove ineffective when the pulsations themselves defy categorization. This leaves astronomers unable to probe what might be happening beneath the star's turbulent surface.
Several dedicated observing campaigns have targeted Alnitak in recent years, accumulating terabytes of high-precision data. The more researchers examine the star, the more anomalies they uncover, including transient spectral features that last only hours and unexpected chemical abundance variations across its surface. Each new finding contradicts some established principle of stellar astrophysics, without offering a comprehensive alternative explanation. This enduring puzzle serves as a reminder that even familiar stars can harbor profound mysteries. Alnitak's refusal to follow established stellar models suggests there are still fundamental processes in massive stars we don't understand. The observations challenge theorists to develop new frameworks that might explain how a star can behave so differently from all known counterparts of its class. While natural explanations will likely eventually account for Alnitak's peculiarities, the investigations have already expanded our understanding of stellar physics boundaries. The star continues to be monitored across the electromagnetic spectrum, with each new instrument offering potential breakthroughs. What began as routine observations of a bright constellation member has become one of observational astronomy's most persistent enigmas. Meanwhile, another distinctive feature of Orion beckons our attention: the vast, glowing arc of Barnard's Loop, encircling the constellation's brighter stars. Stretching across the northern expanse of Orion, Barnard's Loop forms a ghostly arc large enough to swallow dozens of full moons. This faint reddish glow spans approximately 10 degrees of sky, a physical structure over 300 light-years across in reality. The nebula's delicate filaments only reveal themselves in long-exposure photographs, appearing as a cosmic afterimage surrounding Orion's familiar stars. The loop's sheer size presents an immediate puzzle. Structures this large typically form from violent cosmic events, yet Orion shows no definitive evidence of recent catastrophes capable of creating such an expansive shell. Some researchers propose it's an ancient supernova remnant, dating back 2 to 3 million years, when massive stars in Orion's belt reached the ends of their lives. Spectral analysis shows the gas contains elements like oxygen and sulfur in abundances consistent with stellar explosions. However, competing theories suggest the loop might instead be shaped by stellar winds. Orion's young, massive stars emit powerful outflows that could, theoretically, sculpt such structures over time. Observations reveal the nebula's expansion rate matches predictions for wind-driven bubbles. Yet this explanation struggles to account for the loop's full energy budget. Current star formation in Orion appears insufficient to maintain the structure's glow over such vast scales. New radio observations complicate the picture further. Some sections of the loop emit peculiar non-thermal radiation, suggesting the presence of high-energy particles. These could originate from past supernova shocks still reverberating through interstellar space. The recent discovery of several neutron stars, stellar corpses left behind by supernovas in the region, lends credence to this scenario. The loop's morphology hints at multiple formation mechanisms. Some regions show clean, circular edges characteristic of wind-blown bubbles, while other segments appear fractured and distorted. This patchwork structure implies the nebula may result from several overlapping events, rather than a single cause. Tracing the motions of different gas components could help unravel this history. Deep infrared imaging reveals the loop connects to other nebulous structures throughout Orion, forming an intricate web of interstellar material. These connections suggest the loop constitutes just the most visible part of a larger complex shaped by successive generations of star formation and destruction. The Orion Eridanus superbubble, an even larger structure stretching beyond the constellation, may share related origins. Chemical signatures within the loop provide clues about its history. Certain regions show enhanced concentrations of heavy elements that form primarily in supernova explosions. Others contain molecules like molecular hydrogen and carbon monoxide that typically occur in undisturbed clouds. This chemical diversity implies some parts of the loop formed recently, while others preserve material from before Orion's current stars existed. One striking feature of Barnard's Loop is its apparent alignment with Orion's belt stars. The arc seems carefully positioned around these bright markers, though this is likely a perspective effect from Earth's viewpoint. In 3 dimensions, the stars lie at varying distances from the nebula, with no physical connection beyond belonging to the same galactic neighborhood. The loop's temperature measurements reveal another anomaly. Diffuse nebulae typically exhibit consistent temperatures throughout their structures, but Barnard's Loop shows significant variations. Some regions reach over 10,000 degrees Kelvin, while others remain below 2,000 degrees. This thermal inconsistency challenges models predicting how such large structures should behave as they evolve. Age estimates for the loop vary widely, depending on measurement techniques. Studies using expansion rates suggest it could be as young as 500,000 years, while chemical abundance analyses imply ages exceeding 3 million years. This discrepancy might indicate continuous energization by subsequent stellar activity, rather than a single formation event. Polarization measurements offer additional insights. The nebula's dust particles align in patterns suggesting interaction with multiple magnetic fields, rather than the single coherent field expected from a simple explosion or wind model. These complex magnetic signatures could explain some of the loop's structural peculiarities and thermal variations. Some researchers have proposed that Barnard's Loop represents a combination of multiple types of structures, part supernova remnant, part wind-blown bubble, part old molecular cloud. This hybrid scenario could resolve many of the observational conflicts, but requires fine-tuning to match the available data. Simulations struggle to reproduce the exact configuration observed. The loop's ongoing mysteries
highlight gaps in our understanding of interstellar medium physics. Structures of this scale don't form under laboratory conditions, leaving theory as the primary tool for investigation. Each new generation of telescopes brings fresh perspectives, yet definitive explanations remain elusive. As astronomers continue studying this expansive feature, they recognize it as more than just a celestial curiosity. Barnard's Loop preserves information about Orion's star-forming history, while challenging assumptions about how matter and energy interact on galactic scales. Its full story may only emerge as we uncover more pieces of Orion's complex evolutionary puzzle. Meanwhile, the constellation offers additional mysteries deeper within its luminous clouds, particularly within the complex chemistry of the Great Orion Nebula, where scientists have detected organic molecules that shouldn't exist in space.
The Orion Nebula reveals more than just stars in various stages of formation. Hidden within its swirling gases lies a complex chemical factory, producing molecules that shouldn't exist in the harsh environment of space. Astronomers using the ALMA telescope have detected methyl formate, dimethyl ether, and even precursors to amino acids, compounds we typically associate with planetary surfaces rather than interstellar clouds. These discoveries challenge our understanding of how chemistry operates in extreme cosmic conditions. The presence of such fragile organic molecules in a nebula seems improbable. Ultraviolet radiation from young stars should break these compounds apart, yet they persist in detectable quantities. Researchers suspect tiny dust grains act as protective workbenches where molecules can assemble. The grains' surfaces provide both shelter from radiation and a platform for chemical reactions, allowing more complex structures to form than would otherwise survive in open space. Some of these grains appear coated in icy mantles that serve as additional protection and reaction sites. ALMA's high-resolution observations show these molecules aren't uniformly distributed. They concentrate in specific zones where gas densities create natural shields against radiation. The shielded regions function like cosmic laboratories, with temperature and pressure conditions varying enough to facilitate different types of chemistry. Some pockets show molecular complexity rivaling that found in comet ices, suggesting nebular chemistry might seed planetary systems with life's building blocks. Particularly surprising is the detection of molecules with chiral symmetry, structures that come in left- and right-handed versions, like hands. On Earth, life uses exclusively one chiral form of such molecules. The nebula contains both, which raises questions about whether cosmic processes could influence biology's chiral preferences. If similar molecular imbalances exist in other star-forming regions, it might hint at universal tendencies in how life emerges. The detection of phosphorus-bearing molecules adds another layer to the nebula's chemical significance. Phosphorus forms the backbone of DNA and RNA, yet astronomers struggle to explain how it becomes incorporated into organic compounds in space. In Orion, researchers found phosphorus monoxide, concentrated in areas where shock waves from young stars ripple through the gas. These shocks may provide the energy needed to forge phosphorus into biologically relevant molecules. Remarkably, some chemical signatures suggest the nebula hosts types of carbon chemistry thought to require liquid water. Since liquid water can't exist in the nebula's vacuum, astronomers propose alternative formation routes involving grain surface reactions or gas phase processes mimicking aqueous conditions. These pathways could mean the universe manufactures complex organics more efficiently than previously believed. The nebula's chemistry varies dramatically across small scales. In some regions, simple two-atom molecules dominate, while adjacent zones contain structures with 10 or more atoms. This patchwork implies that molecule formation depends heavily on local microenvironments, rather than overall nebular conditions. Mapping these variations helps scientists identify which stellar processes most influence prebiotic chemistry. Infrared observations reveal unexpected molecular emissions that don't match any known compounds. These spectral lines could represent entirely new classes of interstellar molecules, or unusual excitation states of known ones. Some researchers speculate they might be seeing the fingerprints of carbon-based structures too large to qualify as simple molecules, but not quite dust grains, a potential missing link in cosmic chemistry. The nebula's organic inventory carries implications beyond Orion. Similar processes likely occurred in the cloud that formed our solar system, meaning Earth may have inherited its prebiotic materials from such an environment. If nebular chemistry routinely produces complex organics, the ingredients for life could be common throughout star-forming regions, galaxy-wide. Yet for all these discoveries, the Orion Nebula holds structural mysteries that complicate the chemical picture. The same intense radiation that should destroy delicate molecules also shapes the cloud's architecture in ways that aren't fully understood. Towering pillars of gas, violent stellar winds, and chaotic magnetic fields create an environment where chemical models struggle to keep pace with observations. The nebula's heart contains another anomaly, a zone where molecular formation rates defy expectations based on gas density and temperature. This region produces certain organic molecules at 10 times the predicted rate, suggesting undiscovered chemical mechanisms or energy sources at work. Some theorists propose quantum tunneling effects might allow unlikely reactions to occur more frequently than classical chemistry would predict. As instruments improve, each new look at the Orion Nebula reveals greater molecular complexity than anticipated. What began as a search for simple space chemistry has uncovered a dynamic system, capable of manufacturing surprisingly sophisticated compounds. While we've identified many pieces of this cosmic puzzle, their full significance for the origins of life remains to be understood. Meanwhile, deeper in the nebula sits another perplexing feature, the trapezium cluster, where four massive stars orbit each other in a configuration that shouldn't be stable. Their improbable dance challenges our understanding of how multiple star systems form and evolve. At the heart of the Orion Nebula, four massive stars perform an orbital dance that shouldn't be possible. The trapezium cluster's central stars orbit mere light weeks apart, each weighing 15 to 30 times more than our Sun. Such extreme proximity between massive stars defies standard formation models, creating one of stellar astronomy's most persistent puzzles. These stars, Theta 1, Orionis A through D, should theoretically disrupt each other's formation. Current understanding holds that massive stars require substantial space and material to develop. Yet here we find four stellar giants that somehow coalesced practically on top of one another. Their gravitational interactions create a dynamic system more complex than any simple binary arrangement. Computer simulations struggle to recreate the trapezium's configuration. When astronomers model star formation in dense clusters, the results typically show wider spacing between massive members, or rapid ejections of members through gravitational slingshots. The trapezium's relative stability over thousands of years contradicts these predictions, suggesting missing physics in our theories about crowded stellar nurseries. The star's youth adds to the mystery. At just 300,000 years old, infants by cosmic standards, they haven't had time to migrate into this arrangement from more spread-out positions. This implies they formed essentially in place, which raises questions about how a single gas cloud could fragment to produce multiple massive stars so close together without them merging. Spectroscopic studies reveal the stars are simultaneously ejecting material and accreting new matter. Their radiation pressure should theoretically blow away nearby gas, preventing further growth. Somehow they continue drawing material from their immediate environment, despite the hostile conditions created by their neighbors. This challenges standard assumptions about how massive stars reach their final sizes. The cluster's gravitational dynamics present a classic N-body problem with no simple solution. The four main stars influence each other's motions constantly, creating chaotic orbital patterns impossible to predict long-term. Smaller cluster members further complicate the system, occasionally passing close enough to perturb the central quartet's delicate balance. Some theorists propose external forces might have shaped this arrangement. A chance encounter with another dense gas cloud could have compressed the original star-forming material unnaturally tight. Alternatively, the shockwave from a nearby supernova might have triggered multiple collapse sites unusually close together. However, no direct evidence supports either scenario currently. Radio observations show intricate gas filaments weaving between the stars. These structures suggest ongoing complex interactions between stellar winds and remnant nebula material. The resulting pressures may help maintain the cluster's improbable configuration by providing counterforces to gravitational disruptions that would otherwise tear it apart. The trapezium stars exhibit chemical anomalies that hint at unusual formation conditions. Their surfaces show different elemental abundances than typical Orion stars, possibly indicating they formed from a distinct gas pocket with unique properties. This could explain how they avoided fragmenting into smaller stars, as normally occurs in molecular clouds. Infrared monitoring reveals the star's brightness fluctuates unpredictably. These variations don't follow typical young stellar object patterns, suggesting complex interactions between the stars and surrounding dust, or possible episodic accretion events. Each star appears to have its own variation pattern, implying varied environmental influences, despite their proximity. The cluster's radiation shapes the entire Orion Nebula. Their combined ultraviolet output ionizes surrounding hydrogen, creating the nebula's glowing appearance visible from Earth. This feedback effect demonstrates how such compact, massive clusters can influence star formation across vast regions, though we don't fully understand how the clusters themselves form. Future telescopes may reveal clues currently hidden. High-resolution instruments could detect subtle motions, indicating the star's ultimate fates, whether they'll eventually merge, be ejected, or settle into long-term stable orbits. Such data might help identify what physical processes allow such extreme stellar groupings to exist. The trapezium cluster stands as a reminder that nature often defies our neat categorizations. While challenging current theories, it also provides opportunities to develop better models of star formation in dense environments. Each new observation adds pieces to the puzzle, even if the full picture remains unclear. Similar systems have since been found elsewhere in the galaxy, suggesting the trapezium isn't entirely unique. These analogues allow astronomers to test whether common formation mechanisms might exist. However, none match the trapezium's combination of proximity, mass, and stability, keeping it in a class of its own for now. Meanwhile, the cluster continues sculpting its surroundings. Powerful stellar winds have cleared a central cavity in the nebula, giving us an unobstructed view of this enigmatic stellar family. The same radiation that makes them visible also prevents new stars from forming nearby, effectively isolating the system for study. As we examine other parts of Orion, we find additional examples that challenge formation models, like runaway stars moving at incredible speeds that trace back to this region. The trapezium may hold clues to understanding these related anomalies, suggesting connections between different cosmic puzzles within the constellation. Two stars streaking across our galaxy hold clues to Orion's violent history. AE Aurigae and Mu Columbi move through space at over 100 kilometers per second, fast enough to cross the Earth-Moon distance in just over an hour. Tracing their paths backward through time reveals both originated near Orion's belt, roughly 2 million years ago, launched outward in nearly opposite directions. These runaway stars tell us something dramatic happened in Orion's past. The physics behind their ejection presents a puzzle. Normal stellar velocities rarely exceed a few dozen kilometers per second. For stars to reach such extreme speeds requires an extraordinary energy input. Current models point to gravitational interactions in dense star clusters as the most likely explanation. When multiple massive stars orbit close together, their complex dances can fling members outward like stones from a slingshot. Computer simulations suggest a specific scenario that fits the observations. Imagine two binary star systems passing close to each other in Orion's crowded stellar nursery. The gravitational interplay between 4 massive stars could have ejected 2 of them at high speed, while the others either merged or formed a tighter binary. This dynamical ejection hypothesis explains both the star's trajectories and matching ejection times. Proper motion studies support this explanation. Precise measurements of AE Aurigae and Mu Columbi's movements show their paths align with originating from the same region. Their speeds and directions also match what simulations predict from such a close encounter between binary systems. The energy required corresponds roughly to what such an event would release, making this the most plausible explanation among current theories. But mysteries remain. The ejection mechanism would have left behind other stellar remnants near the origin point. While astronomers have identified several candidates in Orion's belt region, none perfectly match the predicted properties of the surviving binary system. This leaves open questions about whether other factors contributed to the runaway's acceleration. The runaway phenomenon extends beyond these 2 famous examples. Several other high-velocity stars in our galaxy have trajectories that point back to Orion. These include 53 Arietis and HD 36960, both moving at similarly impressive speeds. Finding multiple runaway stars from the same region suggests Orion experienced periods of intense dynamical activity when many such ejections occurred. Some research proposes supernova explosions could also contribute to stellar runaways. If one star in a binary system explodes, the sudden loss of mass essentially releases its companion like a slingshot. This mechanism would produce different velocity patterns than dynamical ejections. In Orion's case, the uniform directions of the runaway stars favor the multiple star interaction scenario. The runaway stars carry valuable information about their origins. AE Aurigae's spectrum shows unusual chemical abundances, suggesting it may have been part of a close binary where material transferred between stars before ejection. This forensic evidence helps reconstruct the system's pre-ejection configuration and timeline. Studying these stellar fugitives also reveals conditions in Orion's past. Their existence implies the region once hosted denser star clusters than we see today. The same processes that ejected these runaways would have scattered other cluster members, gradually dissolving the original grouping. This helps explain why we don't see obvious remnants of the presumed massive birthplace. The speeds involved have cosmic consequences. At their current velocities, both AE Aurigae and Mu Columbae will eventually escape the Milky Way entirely, becoming intergalactic travelers. Their eventual fate, wandering the void between galaxies for billions of years, shows how local events can have truly cosmic scale outcomes. Runaway stars also affect their surroundings as they travel. Their powerful stellar winds and ultraviolet radiation create bow shocks in interstellar gas, leaving visible trails that can last for millions of years. These markers help astronomers trace runaway stars' paths and estimate their ages and velocities. The Orion runaways also provide natural experiments in stellar evolution. Isolated from their birth clusters, they offer clean examples of how massive stars develop without neighboring stellar influences. Their predictable trajectories let astronomers study how such stars change over time, with minimal complicating factors. Similar runaway stars have been found originating from other star-forming regions, but Orion's examples remain particularly valuable. Their relative proximity allows detailed observation, impossible with more distant cases. Each new measurement brings clearer understanding of the ejection processes that shaped them. Beyond runaways, Orion contains other stellar anomalies that complicate the picture. The constellation appears to have ejected stars along multiple axes at different times, suggesting a complex history of dynamical interactions. Some lower mass runaways may result from different mechanisms than the massive AE Aurigae and Mu Columbae. Orion's cosmic dust behaves in ways that defy simple explanations. As interstellar particles travel through space, they align themselves perpendicular to magnetic field lines rather than parallel, as most models predict. This peculiar orientation became apparent through polarization studies, where astronomers measure how dust particles twist incoming starlight. The consistent offset from expected alignment suggests our understanding of interstellar material remains incomplete. Detailed mapping reveals the effect varies across Orion's different regions. Near bright stars, radiation pressure seems to influence dust alignment alongside magnetic fields. In darker molecular clouds, the particles show even more pronounced deviations from predicted patterns. These variations imply multiple forces act simultaneously on the dust, creating complex interactions that current theories struggle to model accurately. The standard explanation involves paramagnetic alignment, where spinning dust grains gradually orient with magnetic fields, like tiny compass needles. But Orion's dust shows alignment strengths up to 10 times greater than paramagnetic effects should produce. This discrepancy points to other mechanisms at work, possibly involving interactions between dust grains and interstellar electrons, or unexpected electrical properties of the particles themselves. Quantum mechanical effects may offer partial answers. Some researchers propose that photon interactions at the atomic level could enhance alignment efficiency beyond classical predictions. Laboratory experiments with carbon and silicate analogues show certain quantum states can indeed produce stronger orientation effects. However, replicating exact interstellar conditions proves challenging, leaving open questions about how well these lab results translate to space environments. The dust's composition adds another layer of complexity. Orion's interstellar medium contains a mix of carbon-based grains, silicates, and icy coatings that each interact differently with radiation and magnetic fields. These materials likely originated from previous generations of stars, carrying unique properties based on their formation environments. The variety makes universal alignment predictions difficult, since different grain types may respond distinctly to the same cosmic conditions. Far-infrared observations show alignment persists even where magnetic fields appear weak or tangled. Some dark nebulae in Orion exhibit strong dust polarization, despite minimal measurable field strength. This paradox suggests either our field measurements lack sensitivity or entirely different alignment mechanisms dominate in these regions. The James Webb Space Telescope's mid-infrared capabilities may help resolve this by providing sharper views of dust field interactions. One intriguing possibility involves mechanical forces between grains. As particles collide at modest speeds, their irregular shapes could cause preferential stacking, similar to how wood chips floating in water tend to line up with currents. Combined with magnetic effects, this mechanical alignment might explain some of Orion's observed patterns. However, detailed simulations haven't yet successfully reproduced the full range of observational data. The dust's behavior affects how we interpret other cosmic phenomena. Since astronomers use polarized light to map magnetic fields across galaxies, understanding alignment anomalies is crucial for accurate readings. Unexpected dust properties could mean many field strength estimates require reassessment, potentially altering models of star formation and galactic evolution. Orion serves as an ideal test case for studying these effects. Its combination of bright nebulae and dark clouds presents diverse environments within a relatively compact region. By comparing dust alignment across different zones, astronomers can isolate which factors most influence particle orientation. The constellation's proximity also allows higher resolution studies than more distant targets. Some researchers speculate that dust properties in Orion might be unusual compared to other regions. The constellation's intense star-forming activity continuously processes interstellar material, possibly creating grain structures with unique electromagnetic characteristics. If confirmed, this would make Orion both a fascinating special case and a caution against overgeneralizing dust behavior observed here. The alignment mystery connects to broader questions about interstellar chemistry. Properly understanding dust orientation could explain anomalies in molecular formation rates observed in Orion's clouds. Dust grains serve as platforms for chemical reactions, and their alignment affects how efficiently they shield and catalyze molecule production. Solving one riddle might help address others. New instruments promise to advance our understanding. The upcoming Simons Observatory will conduct large-scale cosmic microwave background polarization studies that could reveal additional clues about dust properties. Meanwhile, advanced spectropolarimeters on ground-based telescopes continue refining measurements of how dust interacts with different wavelengths. What begins as a question about simple particle alignment expands into fundamental physics inquiries. The observed effects might require refinements to our models of electromagnetism on microscopic scales, or force us to reconsider aspects of quantum field theory in space environments. Each unexplained measurement hints at potential gaps in our physical frameworks. For now, Orion's dust remains an active research frontier, where established theories meet stubborn contradictions. As with many cosmic phenomena, deeper investigation reveals increasing complexity rather than quick solutions. The constellation's interstellar particles continue challenging astronomers to refine their understanding of how even small components shape grand cosmic processes. Infrared eyes reveal even more secrets hidden within these dusty clouds. Structures previously invisible to optical telescopes emerge when viewed at longer wavelengths, showing intricate patterns that raise new questions about Orion's makeup and history. Our solar system occupies an unremarkable section of a minor spiral appendage called the Orion Arm. This partial spiral structure bridges the gap between the Sagittarius and Perseus arms, stretching about 3,500 light-years wide. Most galactic maps show it as a spur rather than a full arm, less dense than the Milky Way's primary structures, yet surprisingly active in star formation. The Orion Arm's relative thinness makes its stellar productivity puzzling. Spiral arms typically concentrate gas and dust, triggering starbirth as material compresses in density waves. But this spur contains only about half the average stellar density of major arms, yet hosts numerous active star-forming regions. The Orion Nebula represents just one visible example among many stellar nurseries dotting this galactic bridge. One explanation involves our position relative to galactic density waves. These propagating regions of compressed interstellar matter rotate through the galaxy at different speeds than the stars and gas. As material enters a density wave, it slows and piles up, creating the conditions for star formation. The Orion Arm may represent a region where density wave effects linger after the primary spiral structure has moved on, leaving behind pockets of active starbirth. Recent three-dimensional maps of the Milky Way reveal subtle variations in the Orion Arm's structure. It appears slightly warped in our neighborhood, possibly from past gravitational interactions with satellite galaxies or dark matter concentrations. This warping could explain irregular star formation patterns, as compressed gas follows the distorted contours of the local galactic plane. The arm also shows evidence of past supernova activity, shaping its current environment. Expanding bubbles of hot gas from ancient stellar explosions appear to have carved out cavities that influence where new stars can form. These intersecting shock fronts create complex transitional zones where star formation rates vary dramatically over relatively short distances. Our solar system's location in this active minor arm might be unusually favorable. We sit in a somewhat sparser region, near the inner edge of the spur, protected from the more intense radiation and gravitational disturbances found in the denser galactic arms. This position offers a balanced view of both nearby star-forming regions and more distant galactic structures. Chemical abundance studies suggest the Orion arm has experienced multiple generations of star formation. Older stars show different metallicity patterns than younger ones, indicating progressive enrichment from successive stellar cycles. This layered chemical history provides clues about how the arm accumulated its current structure over billions of years. Measurements of stellar motions reveal another peculiarity. Stars in our section of the Orion arm show less differential rotation than predicted. They move more cohesively as a group compared to stars in denser spiral arms. This unexpected synchronization suggests additional factors, possibly local magnetic fields or dark matter distributions influence dynamics in this region. The arm's alignment offers another advantage for observation. From our vantage point, we look both inward along its length toward the galactic center and outward across its width to inter-arm regions. This gives astronomers natural comparative views of different galactic environments, all within our immediate cosmic neighborhood. Ongoing star formation in the Orion arm follows an irregular pattern compared to classic spiral arm models. Rather than continuous stellar birth along its length, activity clusters in specific zones, separated by relatively quiescent stretches. This patchiness suggests the interplay of multiple factors beyond simple density wave mechanics controls star production here. Astronomers continue debating whether the Orion arm connects physically to larger spiral structures or exists as a separate feature. Some galactic models show it merging with the Perseus arm further out in the Milky Way's disk, while others depict it as an entirely distinct minor arm. Future surveys measuring precise distances to more stars should help resolve this question. The local bubble, an area of sparse hot gas surrounding our solar system, represents another product of the Orion arm's history. This cavity likely formed from multiple supernovae exploding within the arm over the past 10 to 15 million years. Its existence demonstrates how stellar activity continuously reshapes even minor galactic structures. Mapping neutral hydrogen reveals intricate gas filaments threading through the Orion arm. These faint structures trace older pathways of material flow, showing how the arm accumulated its current substance over time. Some filaments appear disconnected from active star-forming regions, suggesting past epochs of star birth that exhausted local supplies. The arm's relationship to the Milky Way's central bar structure adds another layer of complexity. Simulations indicate the bar's gravitational influence can trigger spiral density waves, but precisely how this affects minor arms like ours remains unclear. The Orion arm's current star formation may represent delayed effects from bar-driven shocks that passed through millions of years ago. Understanding our galactic neighborhood could reveal why so many celestial wonders appear concentrated in Orion. The constellation spans regions with varied histories. Some areas contain ancient stars, likely formed elsewhere in the galaxy, while others host brand new stars, condensing from the arm's remaining gas. This diversity makes Orion both a unique observational target and a key to understanding our place in the Milky Way. Orion's dense star fields likely contain thousands of planets we haven't detected yet. With so many stars packed relatively close together, the laws of probability suggest countless worlds must orbit them. Yet, astronomers have confirmed surprisingly few exoplanets in this constellation compared to others. The challenges of planet hunting in such crowded stellar neighborhoods explain part of this discrepancy, but not all. The transit method, responsible for most exoplanet discoveries, struggles in regions like Orion. This technique watches for small dips in starlight as planets cross their sun's faces. In crowded star fields, multiple stars blend their light together, making subtle planetary transits nearly impossible to distinguish. Even when detected, determining which star hosts the planet becomes complicated when hundreds appear in a telescope's view. Direct imaging encounters similar obstacles. While newer telescopes can block starlight to reveal orbiting planets, Orion's dense background glow from nebulae creates additional interference. The same gas clouds that make the constellation visually striking scatter light in ways that obscure potential planetary signals. Most successfully imaged exoplanets orbit isolated stars, not those embedded in complex nebular environments. Radial velocity measurements face different issues. This method detects stellar wobbles caused by orbiting planets' gravity. In Orion, many stars are young and active, their natural brightness variations masking the subtle shifts planets induce. Multiple star systems further complicate readings, as stellar companions create gravitational disturbances much larger than any planet could. The few confirmed Orion exoplanets hint at what we might be missing. One gas giant orbits the star CVSO30, located near Orion's edge. Discovered through direct imaging, it's one of the youngest exoplanets ever found. Another candidate circles TW Orionis, a star still surrounded by its protoplanetary disk. These examples suggest planetary formation proceeds even in Orion's hectic stellar nurseries. Future telescopes could revolutionize Orion planet hunting. NASA's upcoming Nancy Grace Roman Space Telescope will combine high resolution with wide field views, potentially spotting transits missed by previous instruments. Extremely large telescopes, now under construction, might directly image smaller worlds around Orion's stars. Their advanced adaptive optics can compensate for atmospheric blurring better than current systems. The search connects to broader questions about planet formation. Orion's intense radiation environment might affect how planetary systems develop. Massive stars' ultraviolet light could strip away atmospheres from nearby worlds, while frequent supernovae might sterilize emerging planetary systems. Alternatively, these harsh conditions might accelerate planet formation by compressing gas clouds more quickly. Within Orion's star-forming regions, protoplanetary disks show clear signs of planet formation. ALMA telescope images reveal gaps and rings in these disks where young planets likely orbit. Some structures suggest entire solar systems taking shape. The abundance of such disks implies planets should be common here, even if we can't yet detect most of them. Habitable worlds present an intriguing possibility. While massive stars have short lifespans, smaller red dwarfs in Orion could host planets in stable orbits for billions of years. These dim stars are harder to study across Orion's distances, but their sheer numbers make terrestrial planets statistically likely. Water and organic molecules exist throughout Orion's clouds, potentially seeding any suitable worlds. Exomoons around gas giants might offer another venue for life. In Orion's crowded environments, complex gravitational interactions could push giant planets into stable orbits where moons retain liquid water. Such systems would be extremely challenging, but not impossible to detect with future instruments. The James Webb Space Telescope has already examined parts of Orion for planetary clues. Its infrared capabilities penetrate dust that blocks visible light, revealing new details about protoplanetary disks. While not primarily designed for exoplanet detection in dense fields, it may identify potential candidates for follow-up study. Understanding planet formation in Orion has implications beyond the constellation. Its mix of high and low-mass stars in various stages of development mirrors conditions throughout the galaxy. What we learn here could apply to star-forming regions across the cosmos. The relative absence of detected planets may reflect our technological limits, rather than actual scarcity. Radio astronomy offers another potential avenue. Some researchers propose that certain radio emissions could indicate planets with active magnetospheres. Future sensitive arrays might detect these signals from Orion's worlds, bypassing the limitations of optical methods. The TRAPPIST-1 system, though not in Orion, shows what might hide in similar stellar environments. Its 7 Earth-sized planets demonstrate that compact systems can form around small stars. If equivalent systems exist in Orion, current surveys would likely miss them. Orion's exoplanet search ultimately depends on advancing technology. Each new generation of instruments brings capabilities that could transform our understanding. What appears empty today might teem with worlds tomorrow. The same factors making detection difficult — distance, stellar density, and nebular interference — ensure Orion retains planetary secrets for future explorers. Dark matter's influence on Orion's structure might indirectly affect planetary systems. If the constellation contains concentrations of invisible mass, as some theories suggest, its gravitational effects could shape planetary orbits in ways we don't yet understand. This potential connection shows how cosmic mysteries often intertwine. The coming decades should reveal Orion's hidden planets. As instruments improve and methods refine, astronomers will likely confirm worlds in this constellation by the hundreds. Each discovery will add pieces to the puzzle of how planetary systems form and evolve in different galactic environments. For now, Orion's planets remain mostly theoretical, but their existence seems inevitable, given what we know about the universe's planet-forming tendencies. Accounting for these unseen worlds affects how we calculate stellar and planetary populations across the galaxy. If Orion's apparent lack of exoplanets results from observational challenges rather than actual scarcity, we may need to revise estimates of how many planets exist altogether. This constellation's hidden worlds could represent countless missing pieces in our cosmic census. Meanwhile, Orion's other mysteries continue to unfold. The same forces that may shape its hypothetical planets also influence larger structures within the constellation. From stellar motions to gas cloud dynamics, everything connects in this complex region of active creation and constant change. Astronomers tracking stellar motions in Orion have noticed something peculiar. The stars move as if influenced by unseen mass. When they calculate all the visible matter in the constellation, it can't account for the observed gravitational effects. This discrepancy suggests dark matter may be concentrated here more than expected, subtly shaping Orion's structure in ways we're just beginning to detect. The evidence comes from measurements of stellar velocities. Stars throughout Orion move with slightly higher speeds than predicted based on visible mass alone. This excess motion, called velocity dispersion, indicates additional gravitational pull from something invisible. Similar anomalies appear when mapping gas cloud movements across the constellation, creating a consistent pattern of missing mass. Standard dark matter models predict relatively smooth distributions throughout galactic arms. Orion's apparent concentrations could challenge this assumption. One explanation suggests local dark matter clumping from past galactic interactions. Another possibility involves unconventional particle properties, causing dark matter to accumulate near star-forming regions. Both ideas remain speculative, but could explain Orion's gravitational anomalies. Alternative theories propose we might not need dark matter to explain Orion's oddities. Modified Newtonian dynamics, MOND, suggests adjusting our understanding of gravity rather than invoking unseen particles. In this framework, Orion's stellar motions could result from subtle changes in gravitational behavior at low accelerations. However, MOND struggles to explain all observational data as completely as dark matter models. Recent radio telescope surveys have mapped hydrogen gas distributions that may trace dark matter's influence. Some filaments show warping inconsistent with visible mass distributions alone. These structures appear shaped by gravitational lenses we can't see, possibly revealing dark matter's fingerprints on interstellar gas. Galactic simulations, including dark matter, produce mixed results regarding Orion. Some recreate observed stellar motions by placing moderate dark matter concentrations here. Others suggest dense gas clouds could account for similar effects without extra mass. The disagreement highlights how Orion provides a valuable testing ground for competing cosmological theories. The potential dark matter connection could explain several Orion mysteries. Gravitational lensing from unseen mass might contribute to the constellation's puzzling dust alignments. It could also influence the trajectories of runaway stars, adding complexity to their already remarkable velocities. Dark matter detection experiments take special interest in Orion. If excess mass concentrates here, it might slightly increase chances of catching elusive dark matter particles. Observatories like IceCube and Xenon monitor for signals that could correlate with Orion's position in Earth's sky. One intriguing hypothesis suggests dark matter might interact differently near star-forming regions. The frequent supernovae and stellar winds in Orion could, theoretically, push dark matter particles into denser configurations. This would require new dark matter properties beyond standard cold dark matter models. Surprisingly, gamma-ray readings from Orion show no clear dark matter signals. Many theories predict dark matter should produce detectable emissions when particles annihilate. The absence of such signals doesn't rule out dark matter here, but may constrain possible particle types and interactions. Future observations could clarify Orion's dark matter relationship. ESA's Euclid Space Telescope will map galaxy shapes to infer dark matter distributions with unprecedented precision. Its studies of nearby structures like Orion may reveal connections between dark matter and star formation we can't currently see. Studies of millennially old light from background galaxies show possible microlensing effects in Orion's direction. The slight brightening and distortions could indicate compact dark matter objects floating through the constellation. These would need to be significantly more numerous than current models allow to explain the full gravitational anomalies. The dark matter mystery connects to Orion's broader context within our galaxy. If the constellation does harbor abnormal mass concentrations, it might influence the Orion Arm's dynamics. This could explain some structural peculiarities that otherwise seem inconsistent with neighboring regions. Some theorists propose that dark matter halos might preferentially form along spiral arms, natural density peaks in galaxies. If true, our position within the Orion Arm could mean we're embedded in such a halo without realizing it. This could affect how we interpret all local dark matter observations. Ongoing surveys measuring stellar parallaxes will provide better 3D maps of Orion's structure. Combined with precise velocity measurements, these could reveal whether gravitational anomalies follow visible structures or trace separate dark matter distributions. Either outcome would significantly advance our understanding. Radio astronomy offers another approach. Certain dark matter models predict faint emission lines from exotic molecular formations. New instruments like the Square Kilometre Array could detect such signatures in Orion's direction, if they exist at predicted strengths. The possibility of concentrated dark matter makes Orion valuable for cosmological study. Rather than peering to the universe's edges, astronomers might find clues to dark matter's nature in our backyard constellation. The answers await more precise measurements and innovative observation techniques. For now, Orion's dark matter connection remains an open question loaded with potential. Whether the anomalies stem from conventional dark matter, new physics, or something else entirely, investigating them pushes our knowledge forward. The constellation that guided ancient navigators may now guide us towards solving one of modern astronomy's deepest puzzles. Meanwhile, some researchers explore even more unconventional possibilities, including the remote chance that intelligence beyond our own could be influencing what we observe in Orion. While lacking direct evidence, such ideas remind us how much remains undiscovered in this familiar patch of sky. Orion's prominent place in human culture makes it a natural focal point for questions about extraterrestrial life. Reports of unidentified aerial phenomena have clustered in directions coinciding with Orion's seasonal visibility for decades. While most have conventional explanations, the pattern raises questions about why this constellation in particular captures our speculative imagination. The alignment could simply reflect its brightness and recognizability, but some researchers suggest more substantive connections might exist. The constellation contains several stars that fit parameters for potentially hosting advanced civilizations. Applying the Drake equation to Orion's stellar population yields interesting probabilities. With thousands of sun-like stars and millions of planets likely existing within its boundaries, basic statistics suggest life could have emerged somewhere in this region. Whether any civilizations reached technological advancement remains unknown, but the raw numbers make the possibility mathematically plausible. SETI initiatives have repeatedly examined Orion for artificial signals. Projects like Phoenix and Breakthrough Listen allocated significant observation time to stars in this constellation. Their targeted searches included sun-like stars at various distances, scanning for narrowband radio transmissions or pulsed signals
that might indicate technological sources. No confirmed detections emerged, but sensitivity limitations mean weaker or infrequent signals could have been missed. Some astronomical anomalies in Orion have drawn particular scrutiny. The unusual light variations of Alnitak, for instance, prompted brief excitement when researchers noted they could theoretically match predicted patterns of directed energy systems, though natural explanations remain more probable. Similarly, fast radio bursts from Orion's general direction sparked discussions about their artificial potential before astrophysical causes were established. The selection of potential targets involves careful methodology. Astronomers prioritize stars similar to our Sun in age and composition, favoring those old enough to allow complex life to develop, but not so old that civilizations might have expired. Orion presents challenges here. Many stars are very young by cosmic standards, though some older stars exist toward its periphery. These senior members receive special attention in the search for extraterrestrial intelligence.
Infrared surveys raise additional possibilities. Advanced civilizations might manipulate starlight using theoretical megastructures like Dyson spheres. Orion's dust-rich environment complicates such searches, as natural emissions can mimic predicted signatures. Still, some regions demand follow-up when their thermal properties diverge from expectations. The difficulty lies in distinguishing between unknown astrophysics and potential technosignatures. Cultural connections between Orion and claims of alien contact form another dimension. Various groups describe mythological or modern encounters linking human origins or visitations to this constellation, while anthropologists explain these as human psychological patterns projecting significance onto bright star patterns. The persistence of Orion in such narratives remains notable. It represents how astronomical features shape imagination across cultures and eras. Scientific attempts to verify extraordinary claims follow standard protocols. When reports suggest unusual signals or phenomena in Orion, astronomers first check for instrumentation errors or known astrophysical sources. Peer review and independent verification become essential before considering more exotic explanations. This careful approach prevents premature conclusions while allowing genuine anomalies to be properly investigated. Theoretical models explore how civilizations might utilize Orion's unique features. Its dense star fields could offer stepping stones for interstellar travel via gravitational assists. Nebular gas might provide raw materials for constructing large-scale structures. While speculative, such models help scientists consider what observable effects advanced technologies might produce, guiding future searches. Searches now extend beyond traditional radio waves. Optical SETI scans for pulsed laser signals that could outshine their host stars briefly, but dramatically. Orion's bright nebulae might help mask such artificial flashes, making detection challenging. New algorithms attempt to distinguish potential signals from background variability across multiple wavelengths.
The absence of evidence doesn't equate to evidence of absence.
Orion is vast, and our searches have barely scratched the surface. Current technology can only detect extremely powerful directed transmissions or massive engineering projects. More subtle signatures would require instruments we haven't yet built or techniques we haven't yet developed. Future possibilities include neutrino messaging or gravitational wave communications, channels that might be preferred by civilizations more advanced than our own. Orion's dynamic environment
could provide natural carriers for such signals, obscured from our current detection methods. As observational capabilities grow, so too will our ability to probe these domains. Philosophical considerations accompany the scientific search. If life exists in Orion, its nature and intentions remain open questions. The distances involved make direct interaction improbable, even if signals were detected. What begins as science inevitably circles back to how we contextualize humanity within the broader cosmos. For now, Orion remains quiet regarding conclusive evidence of extraterrestrial intelligence. The mystery endures alongside the constellation's other unresolved phenomena. Its prominence in our skies ensures continued observation, both scientific and speculative. The same stars that guided ancient navigators may yet guide us toward answering whether we share the universe with others. This enduring question connects to Orion's broader astronomical mysteries. Whether considering its peculiar stars, unexplained signals, or potential for hidden worlds, the constellation offers endless material for scientific inquiry. Each investigation reveals not just facts about Orion, but also reflects our evolving understanding of life's cosmic context. The search continues, with better tools and sharper questions than ever before. Modern telescopes now probe Orion with unprecedented sensitivity. Instruments like JWST examine planetary atmospheres for biosignatures, while radio arrays monitor for artificial transmissions. These projects may eventually provide data that transforms speculation into knowledge, or deepen the mystery further. Either outcome would advance our grasp of the universe. The lack of definitive proof hasn't dulled scientific interest. Orion remains a priority target in SETI's surveys, precisely because the fundamental questions persist. In a cosmos of billions of stars, the search begins with those nearest and most familiar. Orion's combination of proximity, prominence, and puzzling features ensures its continued relevance in humanity's quest to understand our place in the universe. This intersection of science and speculation defines modern astronomy's approach to big questions. Orion serves as both subject and symbol, an actual collection of stars light years away, and a canvas for our cosmic contemplations. Its mysteries span the measurable and the imagined, reflecting how exploration progresses at the edges of knowledge. Practically speaking, the search continues methodically. Each observation campaign eliminates certain possibilities while opening new avenues for investigation. Orion's stars are catalogued, their properties analyzed, any anomalies noted. This systematic approach follows the same rigorous methodology applied to all astronomical research, maintaining scientific standards while pursuing extraordinary possibilities. Theories about Orion and extraterrestrial intelligence ultimately reflect human curiosity more than confirmed facts. They represent one thread in Orion's rich tapestry of astronomical phenomena, joining stellar oddities, cosmic clouds, and dynamic processes that continue challenging our understanding. Like everything in science, the conclusions remain provisional, pending better evidence. What seems certain is that Orion will maintain its hold on our collective imagination As the next generation of telescopes comes online, they'll scrutinize this familiar constellation with fresh eyes, whether revealing new natural wonders or something even more profound. Orion's capacity to surprise us appears as limitless as space itself. The constellation reminds us how much remains unexplored, even in seemingly familiar regions of the sky. This persistence of mystery makes Orion significant beyond concrete discoveries. It symbolizes how science embraces unanswered questions as motivation rather than frustration. In the careful, patient investigation of Orion's secrets, both natural and potentially artificial, we see the scientific method at work, gradually peeling back layers of cosmic complexity. The process matters as much as the answers eventually uncovered. Orion's mysteries won't remain hidden forever. Next-generation telescopes and space probes are being designed specifically to examine this constellation's secrets with unprecedented precision. The James Webb Space Telescope has already begun uncovering new details about Orion's stellar nurseries, but this represents just the first step in a new era of exploration. The upcoming Extremely Large Telescope, with its 39-meter primary mirror, will provide resolution capable of distinguishing planetary mass objects within Orion's dense star clusters. Its advanced adaptive optics system will compensate for atmospheric distortion in ways current telescopes cannot. Combined with infrared instruments, it could reveal protoplanets forming in disks around young stars that have remained invisible until now. Similar advances are expected from the Giant Magellan Telescope and 30-meter telescope projects. Radio astronomy will also take leaps forward. The Square-Kilometer Array, scheduled to begin full operations later this decade, will map Orion's molecular clouds with resolution sharp enough to trace chemical processes at work in planet-forming regions. Its sensitivity could detect faint signals from complex organic molecules that current arrays miss. These observations might reveal how prebiotic chemistry operates in different nebular environments. Space-based missions will complement ground-based observations. ESA's Plato mission will monitor Orion stars for planetary transits with photometric precision unavailable from Earth's surface. NASA's Habitable Worlds Observatory, planned for the 2040s, will directly image exoplanets in Orion and always their atmospheres, analyze their atmospheres for potential biosignatures. These projects specifically target planetary systems in various stages of formation. More ambitious concepts are being considered. Proposed interstellar probes, while still in early planning stages, could theoretically be sent toward Orion within the coming century. Studies examine propulsion systems like laser sails that might accelerate small probes to significant fractions of light speed. Targets would likely begin with closer stars, before considering Orion's more distant systems. However, given Orion's richness of stellar and planetary subjects, it remains a prime candidate for eventual direct exploration. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will provide another valuable tool. Starting in 2025, it will repeatedly image Orion over 10 years, creating detailed motion studies of stars and possible planets. This temporal dimension could reveal subtle changes in protoplanetary disks, variable stars, and other dynamic phenomena that single observations cannot capture. Spectroscopic capabilities will also expand dramatically. Next-generation instruments will measure chemical abundances in Orion's stars and nebulae with precision orders of magnitude beyond current technology. These could settle questions about the region's metallicity variations and how they influence planet formation. Some spectrographs will achieve resolutions high enough to potentially detect atmospheric constituents on transiting exoplanets around Orion's stars. Time domain astronomy will benefit significantly from these new facilities. Orion's variable phenomena, from flickering young stellar objects to potential black hole interactions, will be monitored continuously rather than through sporadic observations. This could catch rare events like stellar mergers or sudden disk instabilities that have previously been theorized but never witnessed directly. Interferometry projects will push resolution even further. Combining light from multiple telescopes, both on Earth and in space, could produce images sharp enough to track gas movements around forming stars almost in real time. These observations might finally reveal exactly how material flows from accretion disks onto protostars, a process currently understood only in broad strokes. Computer simulations continue advancing alongside observational technology. Exascale computing will enable models of Orion's stellar dynamics that include all known gravitational influences simultaneously. These might explain runaway star trajectories more precisely, or predict where to search for hidden black holes. Coupled with observational data, such simulations could recreate Orion's history with surprising accuracy. Public engagement programs are expanding too. Projects like Zooniverse's Planet Hunters already involve amateur astronomers in analyzing Orion data. Future initiatives will likely distribute even more sophisticated analysis tasks, effectively crowdsourcing some scientific work while increasing public participation in discoveries. Several space agencies have discussed dedicated Orion observatories. Concepts include placing telescopes at stable gravitational points beyond the Moon to study the constellation without atmospheric interference or light pollution. Such platforms could operate across the entire electromagnetic spectrum, with sensitivities impossible to achieve from Earth's surface. Private efforts may accelerate certain aspects of Orion exploration. Companies developing advanced space telescopes could turn them toward the constellation as test subjects before studying more distant targets. These commercial observatories might fill gaps between major government-funded missions, keeping research progressing continuously. The combined effect of these initiatives ensures Orion will remain a scientific priority for decades. Each new capability will peel back another layer of the constellation's mysteries, from star formation to potential planetary systems. Answers that have eluded astronomers for centuries may finally come into view through persistent, multi-generational effort. What we learn here won't just satisfy curiosity about one familiar constellation. Orion serves as our local laboratory for stellar and planetary evolution, a representative sample of processes occurring throughout the galaxy. Solving its puzzles will inform our understanding of cosmic development everywhere. The constellations once used for navigation may now guide us toward comprehending the universe's fundamental workings. Science advances through better tools and sharper questions. Orion's case demonstrates how each discovery enables more refined investigations. The constellation we've observed since antiquity still holds surprises, awaiting the proper instruments and methods to reveal them. Future explorers may look back on our current understanding as limited, just as we now see prior generations' views. The coming decades promise revolutionary views of Orion's stellar nurseries, planetary systems, and cosmic structures. Powerful as these new capabilities are, they'll likely raise fresh questions, even while answering old ones. Each step forward in observational technology has historically expanded rather than contracted astronomy's frontier.
suggesting Orion's mysteries will continue unfolding in unexpected ways. One certainty remains: Orion will persist as both scientific subject and cultural touchstone. Its stars will shine for billions of years, continuing to inspire wonder and investigation. Whatever future explorers learn about them, Orion's place in human history seems assured as our gateway to understanding the broader cosmos. The constellation that guided ancient travelers now guides scientific inquiry toward deeper cosmic comprehension. Orion stands unique in human history, a celestial landmark that has guided explorers for millennia while continuing to challenge modern astronomers. Its recognizable shape appears in cave paintings from 30,000 years ago and structures like Egypt's pyramids. Yet this familiar constellation contains more cosmic anomalies than nearly any other patch of sky. Why does this particular arrangement of stars harbor so many unanswered questions? The answer may lie in both celestial mechanics and human psychology. Statistically, Orion presents an unusual convergence of rare phenomena. The odds of multiple massive stars, intense nebulae, potential black holes, and molecular clouds all appearing within such a compact region seem low. Calculations suggest we shouldn't expect another grouping like it within several thousand light years. This concentration provides an exceptional natural laboratory, but also raises questions about whether we're seeing real uniqueness or selection bias in our observations. The anthropic principle offers perspective. We observe Orion's special qualities precisely because Earth's position allows it. Its alignment with our solar system's plane makes features more visible than they would be from other angles. Orion's winter prominence in the northern hemisphere ensures centuries of study, turning its mysteries into self-perpetuating research priorities. Other, equally remarkable constellations may exist, just not where we can notice them as easily. Yet Orion's physical properties defy easy dismissal. The constellation contains multiple O-type stars, the rarest and most massive stellar class. These luminous giants profoundly influence their surroundings, creating conditions for unusual phenomena. Their combined energy excites surrounding gas clouds into visibility, while their eventual deaths as supernovae will seed the region with heavy elements. This stellar density makes Orion intrinsically more eventful than darker stretches of galaxy. Cultural attention amplifies Orion's scientific significance. As one of the first constellations named by ancient cultures worldwide, it naturally became an early focus of astronomical study. Modern telescopes continue this tradition by probing Orion more thoroughly than less famous regions. This creates a feedback loop where Orion's prominence leads to more discoveries, which further cements its importance. Other celestial regions may contain equal mysteries that simply haven't received comparable scrutiny. The constellation's position affects how we perceive its contents. Orion lies along our line of sight through the local spiral arm, compressing hundreds of light-years of distinct features into a two-dimensional pattern. This projection effect makes unrelated objects appear connected, concentrating what nature actually spread across vast distances. The illusion of proximity invites theories about relationships between objects that may have little actual connection. Questions about Orion's uniqueness extend to potential planetary systems. While exoplanets likely exist throughout the galaxy, Orion stars are young enough that any planets would still bear marks of their formation. Studying them could reveal processes that smoothed out in older systems like ours. This makes Orion not necessarily special, but optimally timed for certain investigations. Human perception influences Orion's importance. The constellation's pattern matches the rarity at which mammalian brains recognize shapes, making it just right for our visual cognition. Were our pattern recognition thresholds different, another grouping might seem equally significant. This cognitive bias leads us to imbue Orion with meaning beyond its objective properties. Despite these considerations, Orion continues to produce genuine surprises. New instruments routinely discover previously hidden features, suggesting we've barely scratched its surface. Each generation assumes they've mapped its major features, only for the next to prove otherwise. This pattern shows no sign of stopping as technology advances.
The constellation's role bridges astronomy's past and future. Early astronomers used it to track seasons. We now probe it for clues about stellar evolution. Future researchers will likely employ tools we can't imagine to uncover deeper layers. Orion serves as a constant in this progression, a fixed reference point against which we measure our growing understanding. Ultimately, Orion's significance stems from both objective rarity and our attention to it. The constellation presents a rich combination of phenomena that merit study, while also benefiting from centuries of observational privilege. Whether uniquely special or simply conveniently positioned, it continues offering discoveries that reshape astrophysics. The mysteries that remain ensure Orion's importance will endure. From unexplained signals to questionable stellar behaviors, the constellation refuses to be fully mapped or understood. This resistance to resolution makes it endlessly fascinating, a reminder that even familiar skies contain depths we've yet to fathom. As the next generation of telescopes turns toward Orion, we can expect new questions as well as answers. This dynamic balance between knowledge gained and mysteries remaining defines the constellation's lasting value to science. The same stars that guided ancient navigators. What seems certain is that Orion will continue challenging our assumptions, whether revealing new physical laws or simply more complexity in known ones. The constellation serves as both classroom and laboratory for cosmic education. Its lessons span from practical navigation to theoretical astrophysics, connecting human history with the universe's grand narrative. The constellation reminds us that significance often lies in perspective. Orion appears special because of where and when we observe it, yet also contains genuine uniqueness that exceeds this bias. This dual nature makes it an ideal subject for studying how we explore and understand the universe, always through the lens of both objective reality and human perception. For now, Orion remains where questions outnumber answers, exactly where science thrives. Its stars will continue shining long after we solve current mysteries, posing new challenges for future generations. The familiar pattern we recognize today connects us to astronomers past and future in our shared wonder at the cosmos. Orion has guided human curiosity for thousands of years, yet still holds mysteries we've barely begun to unravel. Its familiar shape connects us to ancient stargazers, while concealing cosmic puzzles that challenge modern science. From unexplained energy pulses to runaway stars, the constellation refuses to surrender all its secrets. New telescopes will soon probe deeper into Orion's stellar nurseries and dust clouds. Each discovery will likely reveal more questions than answers. This is how cosmic understanding grows. The constellation reminds us that progress means embracing mysteries, not just solving them. Thank you for watching this video. Like and subscribe if you want more videos like it. And remember, look up tonight. Those stars have witnessed human history while keeping their own stories hidden, waiting for the next era of explorers to listen.